Welcome to the fifth lecture on refrigeration and air conditioning. This is a continuation of last lecture wherein we have reviewed some of the fundamentals of thermodynamics and the specific objectives of this particular lesson are to introduce methods for evaluating thermodynamic properties, introduce TS and pH diagrams, and analyze some important thermodynamic processes and derive expressions for heat and work transfer in these processes. And at the end of the lesson, you should be able to evaluate thermodynamic properties using equations of state, tables and charts, identify various regimes on TS and pH diagrams, and estimate heat and work transferred in various thermodynamic processes. Now let us look at thermodynamic property evaluation. In order to carry out calculations in refrigeration or in any thermodynamic calculations on processes or cycles, we need to know several properties. Some of the properties can be measured directly. For example, properties like pressure, temperature, volume, specific heat can be measured directly, whereas some of the properties such as internal energy, enthalpy, entropy cannot be measured directly. So thermodynamic relations have been developed to measure properties which cannot be measured directly in terms of properties that can be measured using carrying out some experiments. Let's look at thermodynamic relations. These are the what I am going to show here are the fundamental relations which are obtained using first and second laws of thermodynamics. And the first relation is given by TdS is equal to du plus PdV. This is known as first TdS equation. And second TdS equation is given by TdS is equal to dH minus VdP. And these two relations are very important, and we shall see how we use them. And since these equations contain only properties, they are valid for both reversible as well as irreversible processes. And two more thermodynamic relations can be obtained by defining two new properties known as Helmholtz function and Gibbs function. Now let's look at various methods used for evaluating thermodynamic properties. The methods used are thermodynamic equations of state, thermodynamic property tables, thermodynamic property charts, direct experimental measurements, and formulae of statistical thermodynamics. Now let us look at the first method, what is known as thermodynamic equations of state. They are also known as EOS. And a typical EOS relates absolute pressure P, temperature and specific volume. One of the simplest examples of an EOS is that the specific volume of a solid is a constant. So this is one of the simplest possible equations of state. Next simple equation of state is that for an ideal gas, that is given here, and as you know very well, for an ideal gas the relationship PV is equal to RT holds good, where P is the absolute pressure, V is the specific volume, R is the gas constant, T is absolute temperature, and the gas constant R, as you know, is given by the universal gas constant divided by the molecular mass. And let me just repeat what is an ideal gas. I am sure all of you know that a gas is said to be an ideal gas if the intermolecular forces are negligible, and also the volume occupied by the gas molecules is negligible compared to the system volumes. Under these two assumptions we can call a gas as an ideal gas. And under what are the conditions under which a real gas behaves as an ideal gas, that is given here. A real gas can be approximated as an ideal gas if it has a low molecular mass and its temperature is relatively high and its pressure is low. That means for a relatively low molecular mass, gases at high temperatures and low pressures can be approximated as ideal gases. And for these ideal gases, as you know, we can use the ideal gas equation. So ideal gas equation is one of the simplest possible equations of state. Now let us look at how to evaluate the enthalpy change, entropy change, internal energy change for an ideal gas. So these equations are given here for internal energy change, specific internal energy change, specific enthalpy change and specific entropy change of an ideal gas. The first equation U2 minus U1 gives the specific internal energy change, and it is given by CV into T2 minus T1, where CV is an average specific heat at constant volume, and it is an average value between T1 and T2. And the next equation is H2 minus H1, that is nothing but specific enthalpy change is equal to Cp into T2 minus T1, where Cp is the specific heat at constant pressure, and it's assumed that it is either constant or we are taking an average value for the interval T1 to T2. Next, using the first TdS equation, we can find out what is the entropy change of an ideal gas, that is given by S2 minus S1 is equal to Cv on ln T2 by T1 plus R ln V2 by V1. This is obtained using first TdS equation, and then using the second TdS equation we can also find out entropy change in terms of Cp and pressures, that is given by S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. And as you know very well, the difference between Cp minus Cv is equal to gas constant. And one thing is I am sure that you remember that for an ideal gas the internal energy and enthalpy are functions of temperature only, and from the equations you can see that the internal energy change is given by Cv into delta T, and for ideal gases Cv is only a function of temperature. So overall the internal energy change is only a function of temperature. Similarly, the enthalpy change is also a function of temperature only. Now let us look at real gases. Ideal gas equation cannot be applied for gases with complex molecular structure, and you cannot apply the ideal gas assumption also when the gases are at high pressure and low temperatures, and when the gases approach the saturated vapor region. That means under these conditions, if you are applying ideal gas equation, it will result in significant errors. Then how do we handle these situations? For these situations we have slightly more complex equations of state, which are even the more complex are more accurate. Let us look at some of these equations of state, typical equations of state. The first one, as you know, is what is known as van der Waals equation, and it is given by P plus A by V square into V minus B is equal to RT. So if you compare this equation with the ideal gas equation, you find two differences. Instead of P, we have added a term A by V square to the pressure, and this term A by V square accounts for the intermolecular forces between the molecules. And the second difference is the term B. Instead of writing V, we have written it as V minus B, and this B accounts for the volume occupied by the gas molecules. So A by V square term accounts for the intermolecular forces, and the term B accounts for the volume occupied by the gas molecules. And it can be shown that for a particular gas the constants A and B are related to the critical properties. That means you can express A and B in terms of the critical temperature, critical pressure and critical volume. And the next equation of state is what is known as Redlich-Kwong equation. This is again, if you compare, this is slightly different from van der Waals equation. Again you have here P is RT divided by V minus B minus A divided by square root of T into V plus B. Again you have the form is slightly different, and we have introduced two new constants A and B, and similar to van der Waals equation, these constants A and B are functions of the critical point and also the nature of the gas. Similar to this, we can have many more equations of state. People have developed many more equations of state which are suitable for certain conditions and for certain working fluids, etc. For example, we have what is known as a RKF equation, which is a modified Redlich-Kwong equation. Similarly, we have another very popular equation known as Martin-Hove equation. So these equations we will be discussing again when we discuss refrigerant property evaluations. Let us look at one general equation, what is known as virial equation. This virial equation is given by PV is equal to RT plus A by V plus B by V square plus C by V cube plus etc. I mean that means you can go on adding terms, and these constants A, B, C are known as virial coefficients, and they are functions of temperature only, and they have to be evaluated using experimental data. So this is one form of what is known as a virial equation. And as you can see, if A and B and C become 0, then this virial equation boils down to a simple ideal gas equation of state. So this equation is very useful, and the equation of states along with thermodynamic relations are used to obtain relations for properties that cannot be measured directly in terms of properties which can be measured directly. I am sure that you have studied this in your basic thermodynamics courses, and for more details you can refer to any standard thermodynamics book. Now let us look at properties of pure substances. How do we define a pure substance? A pure substance is one whose chemical composition does not change during thermodynamic processes. That means it does not undergo any chemical reactions as it undergoes the thermodynamic process. Such a substance is known as a pure substance. What are the examples of a pure substance? The common examples are water and pure refrigerants. And water and pure refrigerants are very, very important in refrigeration and air conditioning, and we will be dealing with these things very frequently again and again. Now let us look at the property evaluation of pure substances. The properties of pure substances can be shown conveniently on pH and TS diagrams. Let me show a typical pH diagram. This figure here shows a pH diagram. So here you have a solid region and a liquid region and a gaseous region, and you also have interfaces. For example, this is the region in which solid and liquid exist in equilibrium. This is the region in which liquid and gas exist in equilibrium, and this is the region in which solid and gas exist in equilibrium. So this is a typical phase diagram of a pure substance on pH coordinates. That means we have H on the x-axis and P on the y-axis, and these lines show the isotherms. That means constant temperature lines, and the temperature increases in this direction. That means this temperature is greater than this temperature, and you can see that in the liquid region the enthalpy of the constant temperature line is almost vertical, and it remains horizontal in the liquid plus gas region. That means in the two-phase region the constant temperature line is horizontal. Of course, this is in accordance with Gibbs phase rule, and when a pure substance boils or condenses at a constant pressure, its temperature remains constant. That's the reason why it is horizontal here. Again, in the two-phase region, you can see that when the pressure is reduced, the constant temperature lines become almost vertical. That means under these conditions they begin to behave as ideal gases. That's why they will become vertical. And here there are two important points. One is what is known as a critical point. As you know, critical point is the point where the saturated liquid line, that means this line, and the saturated vapor line, these two lines join. So critical point is the point at which the saturated liquid line and saturated vapor line join. This is very, very important, and we shall see later how this influences the selection of refrigerants. And physically, when the working fluids exist below critical point, you can distinguish liquid and gas. That means if you have collected this liquid and gas mixture in a let's say a glass beaker, then a meniscus forms between the liquid and gas phases. Whereas if the working fluid is above the critical point, you cannot make any distinction between liquid and gas, and that region is known as a supercritical region. So there is another important point known as triple point. So as you know, probably the triple point is a point at which all the three phases, that means solid, liquid and gas, exist in equilibrium. So that point is shown here. So this is the typical pH diagram for a pure substance. Now let us look at a typical TS diagram, phase diagram on TS coordinates. So again, this diagram shows a phase diagram on TS coordinates. So you have entropy on the, I'm sorry, it has gone back. You have the entropy on the x-axis and temperature on the y-axis. Again, you can see the solid region, gaseous region and liquid region. And you can also see the liquid, solid plus liquid two-phase region, and liquid plus gas region, and solid plus gas region. And you can also see the saturated liquid line and saturated vapor line, and the critical point and the triple point. The saturation temperature of a pure substance is a function of pressure only. So what do you mean by saturation temperature? Saturation temperature, for example, for a liquid vapor mixer can be defined as a temperature at which the liquid and gaseous phases exist in equilibrium. That means at a given pressure, the temperature at which the liquid and gas phases exist in equilibrium is known as a saturation temperature for the liquid gas phases. Similarly, you can also have saturation temperature for solid liquid or solid gas regions. And the relationship between saturation temperature and pressure is given by an important relation known as Clapeyron relation. The Clapeyron equation represents the dependence of saturation pressure on saturation temperature, and that equation is given here. This is the equation where dP by dt is nothing but saturated vapor curve, a variation of saturation pressure with temperature, and it can be shown that this is equal to latent entropy of vaporization divided by the difference between the specific volume of the gas and vapor. VFG as it is shown here, nothing but the difference in the specific volume of the gas and the fluid. G stands here for saturated vapor and F stands for saturated liquid. So dP sat by dt is given by SFG by VFG, where SFG is the difference between the entropy of the saturated vapor and the entropy of the saturated liquid, and VFG is the difference between the entropy of the saturated specific volume of the saturated vapor and the specific volume of the saturated liquid, and this can be shown to be equal to HFG divided by Vg minus Vf into T. This equation is derived because for the two-phase reason, the entropy of vaporization is nothing but enthalpy of vaporization divided by the temperature, and as you know, for a pure fluid the temperature remains constant, so SFG is nothing but HFG divided by T. So we can write this equation in terms of these equations. Even though this equation looks quite simple, it's very useful because it relates properties which cannot be measured directly in terms of properties which can be measured directly. And the simplification of Clapeyron equation results in, if you are assuming ideal gas behavior, and if you also assume that the specific volume of the saturated liquid is much smaller than the specific volume of the saturated vapor, and the latent heat of vaporization does not vary much with temperature. If you are making these assumptions, you can show that this is nothing but since Vf is negligible compared to Vg, you can drop this term. So this becomes HFG by Vg into T, and T can be written as Vt can be written as P by RT. So using the ideal gas equation and these assumptions, ultimately you arrive at this relation. That means dP sat by dt is equal to P sat into HFG by RT square. Now you can integrate this equation between two states, 1 and 2, and if I am taking a state 1 as a reference state, that means pressure is 1 atmosphere and temperature is normal boiling point, that is my reference state 1, and the state 2 is any arbitrary temperature at which I would like to find out the saturation temperature. That means I am integrating the Clapeyron equation between a reference state of 1 atmosphere pressure and normal boiling point and any arbitrary state T. So you get this equation, and using this equation, this is a very useful equation. You can see that normally normal boiling point can be obtained, and this is the temperature at which you want to find out the saturation pressure. So this is known to you, and this will be generally known, and this can be measured or this will be known. So you can find out using this relation what is the saturation pressure at any temperature T. So this is the usefulness of Clapeyron equation, and this equation also tells you that if you are plotting ln P sat versus 1 by T, you get a straight line, and the slope of which will give you the latent heat of latent heat of vaporization divided by the gas constant. And one thing you must remember here is, here the pressure is expressed in terms of atmosphere, and temperature T should be in absolute, that means in Kelvin, degrees Kelvin. So for pure substances, just now as I said, the saturation temperature is only a function of pressure, and the saturation temperature at 1 atmosphere is called as normal boiling point, or NBP. You know this very well. Now the definition of normal boiling point. Now let us look at typical normal boiling points of some refrigerants. So what is given here is the fluid and its normal boiling point. For example, for the refrigerant R11, the chemical formula is CCl3F, and it has a normal boiling point of 23.8 degrees centigrade. And R12, which as you know is a very popular refrigerant, and its chemical formula is CCl2F2, and it has a normal boiling point of minus 29.8. Similarly, R22 has a normal boiling point of minus 40.8. R134A has a normal boiling point of minus 26.5. Likewise, you can find out the normal boiling points of various refrigerants, and this data is very much available in literature. Now, for pure substances, this is one peculiarity: the boiling point and dew